Hey everyone, thanks for joining us today for our webinar, State of RAPIDS, Bridging the GPU Data Science Ecosystem as part of GTC Digital. Since we're remote, here are some quick tips. To maximize audio quality, try closing other open applications. If your audio sputters or the slides lag, please refresh your browser or try using a different browser. If you encounter any other technical issues or have any questions for our speaker, please let us know in the Q&A tool. While we will try and answer most of your questions during the talk, there will also be time at the end for live Q&A. With that and housekeeping done, I have the pleasure of introducing our speaker today, Josh Patterson. Josh is a Senior Director of AI Infrastructure at NVIDIA, leading the RAPIDS engineering efforts. Today, he'll be discussing the growth in the RAPIDS open source ecosystem. You'll learn about the latest engineering work, exciting new benchmarks, new release features, and the future roadmap. It's a lot to cover, so let's get started. Take it away, Josh.
Thank you, Bohan. And thank you, everyone, for joining. I'm really excited, as always, to talk about RAPIDS. And we've really advanced a lot since we launched in 2018. So when we launched, our goal was to accelerate data science on the GPU end-to-end, from data preparation to model training to visualization. We didn't have all of those features day one, but we had a lot of early building blocks, and the evolution from then to now has really been amazing. And so I wanted to start with talking about the foundations of RAPIDS. RAPIDS is built on Apache Arrow. We needed a columnar data frame that worked with the GPU and really reduced the amount of data conversion between CPU and GPU. And around 2016, Apache Arrow began as a project, and it was a really great building block for data science on the GPU. From there, we built a data frame library, CUDF. CUDF uses CUDA for all of the low-level kernels, and we bind it to Python, and we mimic the PANDAS API. Similarly, CUML mimics scikit-learn, CUGRAPH, NetworkX, and we have integration with a bunch of deep learning frameworks as well as visualization libraries. And so when we started RAPIDS, our first kind of benchmark was the mortgage workflow. It was 200 gigabytes of data. So 200 gigabytes is a pretty large data set for most data scientists. I think the average data size for enterprises is around 70 or 80 gigabytes. So we wanted to show that we could do something more than what people do on average, and we had really great acceleration. Comparing to 20, 30, 50, or even 100 nodes in the cloud, we were seeing pretty drastic speed up. And it was roughly about a 20x dollar for dollar improvement. And this was using our DGX2 at the time, and then multiple DGX1s. By 0.10, we had accelerated RAPIDS even more. So there were not only new functionality, but the library itself had evolved and become faster and more efficient, as we can see in the benchmarks. And so the end-to-end time had roughly improved by 35%, which is really great, doing the exact same thing, adding more features. Typically, libraries slow down, but RAPIDS actually started to accelerate even more. And so now that we fast forward, this week we just started code freeze for 0.14. We'll have a release of 0.14 in a few days. From 0.10 till now, we've really focused on three things: scale, functionality, and community. And if you leave this talk early or you have something else to do, the main thing I really want to make sure that everyone is aware of is RAPIDS was always intended for scale. It wasn't meant to be a single system or a single GPU set of libraries. It was meant to scale from a single GPU to many GPUs inside of a system to many systems. So we were always focused on data center scale. We also wanted to have full functionality. RAPIDS is not just data processing in a data frame and machine learning, but it's graph analytics. And we even added things like cuSignal for signal processing, cuSpatial for geospatial analytics. We have integration to a bunch of deep learning frameworks. We have integration into a lot of different Python communities for things like NLP. RAPIDS is really making sure that people can stay on the GPU as long as possible, and do many, many different things in any order that the end user wants to do. And so data scientists, you all have very demanding requirements, and you want to experiment and try new things, and so you need to have the functionality to do that. And then finally, community. There's just too much work for the RAPIDS open source project to do alone. We've always designed from the beginning to be an accelerator of other frameworks. And I'll talk more about that in a minute. So let's just jump into scale. RAPIDS benchmarking TPCX-BB. So what is TPCX-BB? TPC is basically the leader in benchmarking for data analytics and data science. TPCX-BB measures the performance both of hardware and software on 30 different analytical queries, and it basically mimics things that retailers would do, online store presences, but these workflows are actually very similar to things that you might do in financial services or you might do as a telco. And so there's a really kind of broad-reaching set of benchmarks that do things like, clustering or, click-through analysis or other things that are very useful for many different industries. It's also one of the few TPC benchmarks that starts from disk, does ETL, and then does some type of machine learning. And so this really shows the end-to-end usability of a system. If you have to do ETL and then write to disk, do some type of machine learning and write to disk, do something else and write to disk, the performance is really hindered. And so that was actually one of the biggest movements from Hadoop, because reading and writing from HDFS to something like Spark that's fully in memory, you get this performance improvement. So TPCX-BB is primarily done today in Spark and Hive. And what we're seeing is over the last 2.5 years, there's really only been a 1.5x improvement in performance. And also, there's been a 1.5x increase in cost of the servers used to get that performance. And so really, we're seeing this kind of the stagnation of performance on the CPU. Things aren't getting that much drastically better at the 10 terabyte level. And the whole point of RAPIDS was to basically take all the things that you would do today, map them end-to-end on their GPU, and then allow end users to do that without having to write CUDA. And so let's just, really just kind of jump in. Before I go any further, I want to talk about some of the technologies that we use. We, use BlazingSQL, which I'll talk more about later. BlazingSQL is a SQL engine fully built on RAPIDS. We use Dask. Dask is how we distribute our workload. So RAPIDS is really a collection of kernels that mimic these existing APIs, and then we map them to Dask distributed APIs, so we can then scale this across many GPUs and many nodes. We also use a project called OpenUCX, and I'll talk more about OpenUCX and our roadmap for that later in the talk as well. OpenUCX allows us to leverage hardware acceleration for data movement. So moving data between GPUs inside of the system over NVLink or NVSwitch, and moving data across systems using things like InfiniBand or TCP. And so all the benchmarks can be run at different scale factors. And so we primarily focus on the scale factor 1K and 10K. So 1 terabyte and 10 terabytes. The 1 terabyte scale factor 1K, we can do on a single DGX2. That's 16 V100s inside of a DGX system. And then at scale factor 10K, we actually scale out. We scale out with 17 DGX1s. Those are 8 V100s, 32 gigabytes across 17 different DGX machines, all connected by Mellanox InfiniBand. And as you can see on our results, on the 1K, we're getting a 51x speedup, and that's over a 40x normalized for cost speedup. So, if you had a system and it was a $40 million system, we are now doing the same thing in $1 million worth of hardware. And then when we start to scale out, we're seeing an average of a 12x speedup today, and that's 6x normalized for cost. And so we're just going to kind of spotlight a few different queries. One of the queries, query 3, what is viewed before a purchase? And so here we have to repartition data, we have to compute some aggregate metrics, sort the timestamps, and then run a user-defined function to process this session behavior. And so this uses Dask for distributed. It uses Numba, which is a Pythonic JIT compiler, to compile just arbitrary Python code to run on an NVIDIA GPU. And this whole thing is pure Python and SQL running on our GPUs, and we're getting some amazing performance. Another query is query 18. Are bad reviews correlated with bad sales? Again, we're subsetting the data. For each store, we're doing a regression of the sum of net sales, and then we're going to list all the unique store names and find reviews that include those store names. And so this is a combination of NLP, ML, ETL, and so these queries are very broad-reaching. And so getting this end-to-end performance speed up using pure Python, no custom CUDA, at a 10 terabyte scale is really, really impressive. And so, today we're 6x better dollar for dollar. As we move closer to 1.0, we actually can do much better than what we're doing today. So today we're at 6x dollar for dollar, so over an 80% TCO reduction. In the future, we expect that to grow even more. We can add in things like GPU direct storage. GPU direct storage is a part of Magnum IO. It basically allows us to read data directly from NVMe into the GPU, bypassing that host to device copy across the CPU. The next thing that we really want to focus on is using UCS, not just for communication across NVLink and NVSwitch, but also using GPU RDMA, so remote direct memory access. So this allows us for one GPU to send data to another GPU on another server without having to hit system memory. This is going to drastically improve performance, and I'll have a slide later on showing that as well. And there's also a lot of Dask scheduler improvements that are happening right now in the community, which will further accelerate the scheduling of these very large, DAGs, directed acyclic graphs. And so with the scheduler improvements, reducing the latency of knowing what the next thing to do is, will also further accelerate these benchmarks. So, we believe that there's a lot more room on the table. And so 6x is great today, but we really believe we'll get, closer to like a 95% TCO reduction or 20x in the next couple of months. And so with that, that's the performance side of RAPIDS. That's the scale side of RAPIDS. RAPIDS now has end-to-end functionality to do these very elaborate benchmarks, and it has the functionality. But let's talk about the community. So RAPIDS everywhere. Our goal is really just to make RAPIDS usable and performant as possible wherever data science is done. And that is only possible if we have a very large community. And so we want to integrate RAPIDS into many different projects. We have a great relationship with XGBoost and KuPy and Apache Arrow. We have people that contribute to Dask. We work with the Dask community well. We recently, in Jensen's keynote, we announced that we're working with the Apache Spark community. We have zero interop with PyTorch and MXNet and Paddle. In TensorFlow 2.2, we'll also have DLPack integration, so we can have zero copy interop with TensorFlow. And so the community is just growing and growing and growing, and this is really exciting. And then even within RAPIDS, as I said earlier, we have cuSignal, which honestly I won't be able to talk about today just because of time constraints, and cuSpatial. But if you go to rapids.ai, docs.rapids.ai/overview, you can see our latest deck for each release, which talks more in depth about cuSignal and cuSpatial and all the other libraries that are built on top of RAPIDS. And so let's start with data visualization. When we launched, we had some data visualization integration through Kepler-GL, but recently we've added several new things. So now we have integration with Plotly Dash. It's been really exciting working with the Plotly community. We worked with them to basically amalgamate all the census data with all the COVID data we could find, so we could have an interactive visualization that was population-based, hospital-based, and outcome-based. So decision makers can make better decisions about how to allocate resources. And so rapids.ai /Plotly, you can see more information about how to integrate Rapids with Plotly and see getting started in other use cases. We also have links to Medium blogs about the integration between Rapids and Plotly. We also have native CUDF and Dask CUDF support in Data Shader. We also have a really great blog about that on our Medium, as well as CUX Filter has improved significantly since launch. And so CUX Filter allows you to create these exploratory dashboards essentially a lot easier without having to rebuild all the connections from the ground up. Next, I'm going to talk about CUML. So CUML is our machine learning library. CUML's major themes over the last couple of releases is multi-node, multi-GPU, MNMG. We talk a lot about multi-node, multi-GPU because people need to scale. The new DGX A100 has 40 gigabyte A100s, 8 of them. That's 320 gigabytes of GPU memory, which is phenomenal. But people still have problems that are larger than that. People have, 1, 2, 5 terabyte problems, and so you need to scale to many DGX A100s to solve these problems. And CUML wants people to have all the traditional algorithms at your disposal running seamlessly at scale. And so we've really, really focused on scale in CUML. We've also focused on interop and integration. If you're using NumPy or CuPy or PANDAS, PyTorch, really almost any data science pre-processing, we want that to feed into CUML as seamlessly as possible. And so with the CUDA array interface, we can basically read in data into CUML, and then we can push that data out in a very systematic fashion where it really lowers the overhead of the end user having to think about what's my I/O, what's my input and output. And then also more algorithms and not just algorithms. So more variants of algorithms, more wrappers around algorithms. And we're going to continue to grow this with custom loss functions and better inferencing tools as well. And so our goal is to not only provide more functionality, but also provide a better user experience and some of these quality of life things in our algorithms. Some of our new algorithms in CUML are random forest, TSNE, and support vector machines. The speedups are just kind of mind-boggling. And I love that we have a lot of people using Rapids now in Kaggle. You can basically, inside your Kaggle kernels, use Rapids on those GPUs. And there's a lot of notebooks showing, really impressive speed ups by using Rapids. And so from random forest to KNN is really kind of picking up in the Kaggle space, and we're really excited about that. Support vector machines is currently number 1 in the images trends, neuro trends Kaggle contest right now. There's a great kernel out there, notebook, that shows how to use SVM to basically get pretty top performance. And SVM is an algorithm that basically was so slow. People had almost said, why would I ever use SVM anymore? And so when you make it 500 times faster, it becomes very viable again. And there's no silver bullet. So having more algorithms allows people to find the best model quicker, and sometimes a slower model might actually be the better model. And so once you GPU accelerate it, it then becomes something that you can do interactive and do hyperparameter optimization on. And with that, now you have a lot more tools in your toolkit to basically do better data science. And we're really excited about that. We've also been partnering with the XGBoost community. We have a lot of committers to XGBoost within the Rapids organization. I always want to reiterate the point that we never want to basically consume things. We want to give back to the community. We want to build bridges and not walls. And so we contribute directly to XGBoost. We help with the Dask, an official Dask API within XGBoost. We've helped reduce the amount of memory usage on the GPU in XGBoost. There's learning to rank. And so the RAPIDS committers also commit to XGBoost, and the interop between XGBoost and RAPIDS is really, really great. It's very seamless. And so XGBoost is just another part of our ecosystem that plays very nicely and seamlessly with RAPID. And so, as more and more projects start to evolve and grow in popularity, like Plotly and XGBoost, we want to be there to integrate with them, build bridges, and really kind of extend what people can do on GPUs. And so on our road to 1.0, we want to get several more multi-node, multi-GPU algorithms. This is our current thinking today. So random forest, k-means, KNN, linear, and logistic regression, GBDTs, PCA, and SVD are kind of our main focus. This might change over the next couple of releases, but our goal is to continue to have more and more multi-node, multi-GPU algorithms. We also, through CUML, we started to focus on hyperparameter optimization, HPO. And through this, there was this really great project in Ray called Tune. And so RayTune is a scalable HPO library that really just allows you a really efficient way to find the best model. And so we started working with the Ray community, and now you can use RAPIDS in Ray to do HPO. And not just in Ray, we can do HPO in Dask, we can do it in SageMaker, we can do it in Azure ML, we can do it in Google AI Platform. And pretty much across the board, we're seeing a significant speed up in TCO reduction. So roughly around a 10x, a 7 to 10x TCO reduction. So somewhere between 80 and 90% reduction in cost, as well as it getting to the end result 40 times faster. And so if you want to learn more about HPO, rapid.ai/HPO. And so, again, 7x TCO reduction, significant, speed up as well per iteration. And now on to CUDF. So CUDF is really kind of the backbone library of RAPIDS. Everything kind of connects to CUDF. CUDF is our data frames. If we didn't have data frame manipulation and fast loading of data, really none of this would be possible. And so CUDF is in two levels. There's LIBCUDF, which is our CUDA C++ library. And this allows us to do all these data frame manipulations on the GPU. We then use Python to bind Python to LibCUDF, and this is our CUDF proper library. We use Numba in CUDF to JIT compile user-defined functions, and this basically allows people to do pandas-like things on the GPU. And so just a simple comparison, doing things like a merge or a sort or a group by, it's somewhere between 300 to 900 times faster on a single V100 than a pretty beefy multi-core CPU. And most people think about numerics and matrix multiplication and things that GPUs are traditionally good at. We also built a full string library inside of CUDF. And so originally it was a separate library, CUStrings and NVStrings, that's fully within CUDF now. And so CUDF has some really amazing string support. It has a native string type in libcudf C++, and it's, again, 50 to 100 times faster than other string libraries. In 0.14, we further improved the performance and a lot of optimization of CUDF strings, and then also allowing a user to JIT compile string UDF, user-defined functions. And so earlier I was talking about not only data processing, but data loading. CUDF has a full I/O library as well. And so we can read in things like CSVs, which we had at launch. We can now write CSVs out, which was in version 8, 0.8. We can read Parquet, we can write Parquet, we can read ORC, we can write ORC, we can read JSON, Avro, and in 0.15, we're going to add a Kafka source sync. This is going to be really important for stream processing, which I'll talk more about later. We're also going to integrate GPU direct storage in the near future to bypass a lot of the PCIe bottlenecks. And we're seeing some pretty remarkable performance. Here on the right, it's roughly a 15x acceleration for reading in a CSV. Now we start thinking about multiple GPUs and multiple, compared to multiple CPUs. A system like a DGX A100 has 8 GPUs. Each one is 15 times faster than the 2 sockets on there. And so you get some really big I/O advantages by moving to GPUs for I/O. And LibCUDF is not just meant for Python. Even though we have Python bindings to Python, other things are now using LibCUDF, one of which is BlazingSQL. BlazingSQL is an open source SQL engine built fully on top of RAPIDS. It integrates with all of RAPIDS, so you can go from BlazingSQL into CUDF, CUML, or CUGRAPH, even CUSignal or CUSpatial. And they are doing some really amazing things with out-of-core and optimization at the relational algebra engine level, so they can shuffle data in and out of the GPUs very efficiently. So for TPCH at a 1K scale factor, running on just 8 GPUs. And so this is a 1 terabyte scale factor running on 256 gigabytes of GPU memory, is basically about 7x faster than Presto running across 11 R4.8 instances on AWS. And so what's really impressive about this is it's still faster in just raw time, and it's also almost an order of magnitude cheaper to move to the GPUs. And this is just on a single system. Being fully built on RAPIDS, they have TCP and UCX integration, and as RAPIDS starts to add more things, so will BlazingSQL, and it will just natively get faster over time. So coming in 0.14, as I said, we're just entering code freeze today for 0.14. So in the coming release, and in 0.50 and more, and on forward, we did a lot of things to improve our API documentation. Legacy libcudf has been completely removed. NV strings is completely deprecated, and internally we called it the Great libcudf++ port. So we've moved into this new libcudf that's more similar to a C++ library. We've removed NV strings completely, and we've put all of it back into a libcudf that's just better for more libraries to connect to it. And I'll talk more about one of the big libraries at the end that's now connecting to it, but it's improved things like BlazingSQL to have better string support and lower latency. And we're really excited about kind of our first major deprecation within side of RAPIDS, removing legacy libcudf and moving into libcudf++. In 0.15, our goal is to have CUDA 11 and Ampere support. So CUDA 11 is soon going to be GA, and the Ampere GPUs, the A100, was just announced a few weeks back by Jensen, and we're really excited about A100. And so we want to make sure that as soon as they're available to end users, people can use RAPIDS on them. We're also going to expand data types, unsigned integers, dictionary, nested lists and structs. So a lot of things coming for CUDF in the near future. And we're going to also optimize some of the I/O for handling small files and partition data sets. So many more optimizations coming in the future, more documentation, more API stability. We really want CUDF to be the backbone of future data frame libraries. So CUGRAPH. So we have a lot of functionality in CUGRAPH. We have many algorithms. Compared to NetworkX, we're seeing, honestly, about 1,000x improvement. And so NetworkX is a pure Python graph library, dozens of millions of downloads annually. And we're systematically going through and writing CUDA versions of those algorithms and then binding them to a Python interface that is quite similar to NetworkX. And some really amazing speedups. There's a lot of blogs on Towards Data Science, our own Medium, and others showing, almost interactive graph performance by using CUGRAPH. The one that kind of keeps coming up over and over again is PageRank. And so PageRank is just notoriously slow at really large scale. And so at 10 nodes, 25 nodes, 50 nodes, and 100 nodes left to right, you see this kind of time of improvement of PageRank iterations. And then if you run that on a single DGX2, it's about 10 seconds. And so there's a massive speed up of PageRank, one of the backbone graph analytics algorithms for a lot of recommenders, by moving it to GPUs. One of our limitations with PageRank, though, is our first implementation of PageRank was a single node multi-GPU, SNMG. And so our limit was really about 300 gigabytes of data. And this is why we stopped at 16 GPUs on the DGX2. Fast forward, we started working with the DGX A100s, and our future PageRank, which we're aiming to have fully released in 0.15 of RAPIDS, phenomenal performance. Multi-node, multi-GPU, 32 A100s. We're getting iterations down for a 5 terabyte graph, down to 0.18 seconds. Comparing this to really a very optimized PageRank implementation that Yahoo did on 3,000 or up to 3,000 nodes, they were getting about 2.45 seconds per iteration. So an order of magnitude improvement, and 2 orders of magnitude less hardware. 3,000 to 32 GPUs is astonishing. And the great thing about this one is we can continue to scale this out even further to 64 A100s or 128 A100s. And this is really exciting. I'm really proud of the graph team, the CUGRAPH team, moving from single GPU to single node multi-GPU to multi-node multi-GPU. Is a lot of is a Herculean effort, and they've done a great job. And I think the community is going to be really excited about running these algorithms multi-node multi-GPU in 0.15. And so we've updated the roadmap for CUGRAPH. 0.15, PageRank, personal PageRank, and breadth first search, BFS, multi-node multi-GPU. And we have many more multi-node multi-GPU algorithms following basically the same path that the single GPU did in earlier versions of RAPIDS. Same priority. So SSSP in 0.16, Louvain in 0.17. We're going to continue to add new single GPU algorithms as well. And then we're going to do some refactoring and cleanup, better documentation support, and API stability across these versions as well. And so now let's talk about UCXPy. UCXPy and NVLink are so critical and so important to RAPID. I can't really explain, the gravity of really fast data movement. Big data is, big. So we need GPUs. And the GPU bandwidth inside of the GPU is really, really high. The PCIe bandwidth is not. And so we had to figure out ways to move data very quickly across GPUs. One thing is don't move data as much and have a really, really smart algorithm that try to do as many things locally as possible. But eventually we have to scale out, we have to move data, and we wanted a way to move data between GPUs inside a system as well as external to a system as efficiently as possible. And so our solution is UCX. One of the great things about UCX is it's one library that works both inside a system as well as external to a system. So the UCX library handles both NVSwitch, NVLink, as well as InfiniBand and TCP and other communications. And so OpenUCX, it has a lot of people contributing to it, notably Mellanox. Mellanox spends a lot of time on OpenUCX, and we're really excited about Mellanox becoming a part of NVIDIA. And so with this, the OpenUCX community, we've been working with them to extend UCX to Python, so UCX-Py. It's just some really great work. And so when you look at the theoretical limits of what we should be able to do with NVLink and Mellanox InfiniBand, and what we're getting with UCX-Py, even putting a Python wrapper around it, we're almost hitting theoretical limits of performance. And so we're basically moving data in Python as fast as we possibly could across these optimized networking fabrics. And so for a merge benchmark, we're doing a distributed joiner merge from 2 data frames of random data, 2 columns, 30% matching on a single DGX1, which I'm going to jump back a few slides. Sorry, that's NV switch topology. We're getting about 17.4 if you're using both InfiniBand and NVLink. 11.7 gigabytes per second bandwidth if you're just using InfiniBand. 3.9 if you're just using NVLink, and so forth and so on. If we change the network, if we go from NVLink to NVSwitch, which NVSwitch has an all-to-all communication across the GPUs. And so the DGX A100 has an NVSwitch for 8 GPUs, just like the DGX2 had NVSwitch across 16 GPUs. So we only use the first 8 GPUs of a DGX2, which is similar to a DGX A100. What we see is the NVLink bandwidth jumps up to 37.7, 17.4 for InfiniBand plus NVSwitch, 11.7 for InfiniBand alone, and so forth and so on. And so here, 11.7 for InfiniBand. Now it's in purple, still 11.7, but we get more bandwidth by just changing the network topology. What's really exciting is the DGX A100 has twice the bandwidth of a DGX2 per GPU. And so we're going to see even more of a significant bump on the DGX A100 NVSwitch bandwidth for things like merges. And so, actually, I'm going to go back one more time. All of this is going to further allow TPCX-BB to get even faster. And so we're really excited about not only getting the Mellanox InfiniBand support for RDMA across nodes, as well as in 0.15 doing DGX A100 bring up and CUDA 11. All of these things combined, we really think we're just going to have some really great results and have even better dollar-for-dollar performance on these kind of standard benchmarks. And we spent a lot of time talking about big data, batch processing, machine learning, ML inference. And it made us realize that we should also talk about stream processing, so we can do essentially streaming ETL. And so internally, there's a team that's a production big data team. They take all of our streaming data internally, and it feeds into different distributed systems, and they do real-time monitoring. And it's really important that they can, stream data as fast as possible to have real-time analytics so NVIDIA can make business decisions. The amount of data is growing, especially as more and more people work from home, as more and more people use online services. And so the cost of streaming is growing. it was really important for us to move this to the GPU. And so we initially moved it to the GPU, and then we saw some performance benefits of moving to the GPU early on in phase 1. We had very low GPU utilization. And so we were at basically 5% GPU utilization. In phase 2, we basically did better JSON preprocessing, which CUIO has a JSON reader, snappy compression on Kafka. We started adding in multiple Dask workers per GPU. And we got up to 95% GPU utilization. We had a drastic improvement in our throughput per GPU, and these are T4s. In this example, the G4DN is a T4 instance on AWS, but we're still using about 24 cores. In our most recent one, we doubled the throughput, and we cut the number of CPU cores by a third. So the cost of running this almost went down by 50%, and we doubled the throughput to 600 megabytes per second. And so half the cost, twice the performance. And one of the big things for this is we added something called LIBRD-Kafka, Lib Remote Direct Kafka. So we can read directly from Kafka into CUDF, and this really allows us better Kafka integration, better performance with fewer CPUs, and we're really excited about cuStreams. Using cuStreams internally is saving us money today, and we're going to have several blogs coming out about this in the next couple of weeks, and this will be fully integrated in 0.15 into RAPIDS. And so the first step for GPU streaming really is around accelerating Kafka. And so with LibRD-Kafka, we're getting this 25x speed up for moving data from Kafka into CUDF. And that's really kind of the main point, and was one of our early bottlenecks. In the future, we're going to add some more functionality to cuStreams, a publish once, compute many, rolling data frame windows, and rolling data frame events. One thing that I forgot to mention is initially Streams, which is built on Dask, it wasn't stateful. And so, another example of us contributing back to the community, we contributed a way for Streams to be stateful, which was really important for our internal use case. And again, building more bridges to communities, there's a lot of work that if we had built this from the ground up, it would have taken a lot longer versus using something that already existed in the Dask community. And next, I'm going to talk about our Cyber Log Accelerator, so CLX. So CLX is really a way to take all of the things in RAPIDS, CUDF, CUML, CUGRAPH, as long as BlazingSQL and some other GPU packages, and have really great examples to show security analysts how to use GPUs with their existing SIEM, whether that's QRadar or Splunk or VMware or Elk. And so we have several use cases. Some are still in the proof of concept stage. Some are stable and getting deployed at customers. And we're going to continue to evolve this. And so if you go to RAPIDS GitHub page and go to the CLX repo, there are several different use cases and integration and kind of quick starts to these different cybersecurity applications. And the goal is to really kind of have this buffet of different things that people can do so they can use GPUs faster and more seamlessly with whatever SIEM tool that they're using today. One of the things I really love is CyBERT. So there's a lot of talk about BERT for NLP and question answering and essentially summarization of dense text. But we can also use BERT as a regex engine, essentially. So we've trained this BERT model to parse these log events, and we're getting over a 0.999 accuracy, and a very low loss. And what we're able to do is basically train a neural network to read in batches of logs and parse them into a more usable format, so we can do things like group bys and merges and all these other things that CUDF does and feed them directly into CUML and CUGRAPH. We also have a tokenizer. So when you have a long sentence, you want to be able to tokenize this. Hugging Face's tokenizer is kind of state-of-the-art. And right now, the tokenizer that we built for clicks is about 270 times faster when you're using really large batches, and even 10 times faster with a batch size of 100. So 100 sentences or 100,000. You're still getting this improvement. And what this is really useful for is we can do this tokenizer, and then we can pipeline directly into PyTorch or CUML or CUGRAPH or whatever you want to afterwards. And so it really kind of just fits right into your data science pipeline. Also, this is the only WORDPIECE tokenizer that supports non-truncation of logs or sentences. So it can be arbitrarily long as well. It doesn't have a character limit. And so we really wanted to have optimal flexibility as well as performance. And then finally, rapid acceleration for Apache Spark. Jensen announced rapid acceleration for Apache Spark 3.0 in his keynote, and we're really excited about extending the Rapids community to the Java community. And so most of what we talk about in Rapids is very Pythonic. This is a new area where NVIDIA and the Rapids engineering team and the community are all coming together to accelerate Spark, so rapid acceleration for Spark. Today, we're focusing on Spark SQL and the data frame API. And so remember earlier when I was talking about moving from legacy LIBCUDF to LIBCUDF++, this allows us to map Java and Scala to C++ better through JNI, Java Native Interface bindings. And so now we can have the exact same Spark code run, and if the GPU is enabled, it runs on the GPU. If not, it gets executed by standard Spark. And so it's literally a drop-in replacement for Spark to run GPU accelerated code. We've been working with the Spark community to improve Spark Shuffle, to have UCX support, so the Java bindings for UCX. This is an ongoing effort. There is an alpha right now. If you go to NVIDIA.com, there's a lot of backslashes there, but eventually Spark, Apache Spark 3, you can sign up for the alpha and also get more information about upcoming releases. This is an ongoing effort, and we're really excited about working with many in the Spark community, including Databricks. And so the Rapids roadmap. In 0.14, that's being released in a few days, we spent a lot of time focusing on a lot of quality of life things, bug squashing, documentation improvement, reducing technical debt, removing legacy code like LIBCUDF, so forth and so on. But yet we still added some new multi-node, multi-GPU algorithms, the CUML array support, and more. In 0.15, we're going to do Ampere and CUDA 11 bring up. We're going to have more multi-node, multi-GPU algorithms. We're going to have both in CUML and CUGRAPH. CUDF is going to have nested type, column list support. And so there's a lot of things that are going to happen in 0.15. And then beyond, we have some really exciting things on the roadmap, like SHAP explainability, GPU acceleration, matrix factorization, more multi-node, multi-GPU algorithms for CUML and CUGRAPH, and also expanding the pre-processing for machine learning as well. So that was a lot. I'm pretty exhausted. So join in. If you haven't used Rapids before, you can get the source code on GitHub. It's fully open source. You can PANDAS install Rapids. You can get Rapids from NGC or Docker Hub. Rapids runs on SageMaker, Azure, ML, Google Cloud AI Engine, and it runs on many other clouds. Pretty much any cloud that can run NVIDIA GPUs, you can run Rapids. And we also have the Rapids release selector, where depending on your environment, the version of Python you want to use, your operating system, you can get a simple command to install Rapids. So join the community. we're adding more visualization, more machine learning, more, scale out data preparation. And the loop only gets faster as we integrate with more frameworks and libraries and solutions. And we get more developers kicking the tires and using it. It's been used in production by many companies. There's some really great articles on our Medium and other mediums and just blogs in general about the savings from Rapids. If you go to rapids.ai, there's a list of companies contributing to Rapids, adopting Rapids, using Rapids. And we're really kind of excited about just the growth of the community. So thank you. Follow me on Twitter. If you have any other questions, jump on the Rapids Slack in the rapids.ai/community. There's a link to our Slack as well. Join our Slack and feel free to ask any questions.
Thank you, Josh. Appreciate everything. Amazing amount of information, and I know we covered a lot. So if there's any additional questions, please use the Q&A tool at the bottom, and we'll take live Q&A with Josh right now. I'm going to kick it off with one question that we had. Josh, I'm interested in trying out Rapids proof of concept, but I have a bunch of different projects on my team. What's an example of a good type of workload that's easy to get started porting to Rapids?
That's a great question. If you have any, PANDAS to scikit-learn workflows, I think those are some of the easiest to start with. We have really great coverage of the PANDAS API, and we have almost all the core algorithms covered. And we also have a lot of starter notebooks on GitHub as well. And so really, I would just look through some of the notebooks that we already have and see what's the most similar to what you're doing. That'll probably take a few minutes. And then just conda install Rapids in an environment. You can either use Google Colab or apps.blazing, or get a T4 for about 50 cents an hour on GCP or AWS and get started. There's some other questions here. Oh, no worries, Michael. Any plans to incorporate Windows support? Yes, this is a great question. I see that Brad said that we were working on integrating within the Linux support layer within Windows. I could add a little bit more. Microsoft recently announced that WSL, Windows Subsystem Linux, is adding CUDA compute support. We have been doing testing of Rapids on that, and as soon as that's more widely available, we'll have more information on how to basically launch Rapids with WSL on Windows. And so soon, it should be very easy to use Rapids and any other Pythonic library on Windows through WSL. So all the work that we've done, you can have your great Windows GUI and just launch it in a Linux VM on Windows. Where can I go to learn more about Rapids and continue to engage with the Rapids community? This is a great question. Rapids.ai is a great place to learn more about Rapids. It will link you to our blogs, medium.com/rapidsai, to our GitHub, and as well as to our Slack. On GitHub, you can ask technical questions, file issues, bugs, feature requests. On our Slack, you can ask more interactive questions that you might have. Where can I find examples of how to use Rapids? So again, Medium is a great place. There was even a blog today on Towards Data Science about using the Taxi notebook and XGBoost and Rapids for pretty drastic speedups. We have about 5 blogs a month and a lot of examples within all those blogs. We also have GitHub that has a lot of examples in each repo, as well as Rapids examples.
There's 2 more questions in the inbox, one on Spatial and BERT you can get to.
Great. Where do I get the Rapids BERT doc? Go to CLX. So on the GitHub page, there's CLX. If it's not in the 6 pinned, it's pretty easy to find. And then within the CLX repo, there is more documentation on Cyber. what is the timeline for standard distance and standard contains and CUDA spatial? That's a great question. I think this is one of those times we're going to say file an issue. If you already have an issue open, just bump me or T on GitHub, and we will ping the team to figure out when that's going to be on the CUDA spatial roadmap.
Last chance for questions for Josh. Get them in now. All right, we'll close out our Q&A. Thanks again for joining us. An on-demand version of the webcast will be made available approximately 1 hour and can be accessed using the same link. This link will expire in 48 hours. So after that time, you may access the replay within the GTC session catalog. The PDF of the slide deck will also be made available in the catalog. So go check it out. Thank you again for joining us, and have a great rest of your day.